Lina.
My name is Farah Alia.
My name is Lakshita Manashri.
I'm Shahira Iliana.
This video is for our analog electronic assignment and we are from group
E.
Okay, today we'll be introducing the Wien bridge oscillator, a well-known circuit used to generate the pure sine wave.
It was developed by Ms. Wien and it based on special type of Wheatstone bridge called the Wien bridge network.
This oscillator is widely used because of its simplicity, frequency stability, and low distortion output, especially for audio signals.
It typically uses an op-amp with a positive and negative feedback to control the amplitude and frequency of the output.
At its resonant frequency, the circuit provides zero phase shift, producing a smooth and clear sinusoidal waveform. Let's dive deeper into how it works.
Let's go!
First and foremost, let's get to know the circuit diagram for the Wien bridge oscillator. Based on the figure shown, resistors R1 and R2 along with capacitors C1 and C2 form the frequency adjustment elements, whereas resistors R3 and R4 form part of the feedback part. The op-amp output is connected as the bridge input at points A and C. The bridge circuit output at points B and D is the input to the op-amp. The circuit consists of two main sections, which is the amplifier section using the negative feedback and Wien bridge network using the positive feedback. Firstly, for the amplifier section, the op-amp is set up as a non-inverting amplifier using resistors R3 and R4. This means the op-amp increases the input signal without flipping its phase. It also controls the overall gain of the oscillator to keep the output stable. As for the Wien bridge network section, it consists of series RC circuit with R1 and C1 and also a parallel RC circuit with R2 and C2. Together, these components create a frequency selective feedback network. This network determines the oscillation frequency and provides the necessary phase shift for the oscillation. To conclude, the op-amp amplifies the selected signals and sends it back through the bridge. As long as the gain is just right, the circuit keeps producing a clean, steady sine wave, no input signal needed. This is how the Wien bridge oscillator uses both positive and negative feedback to generate and control sine wave signals.
Ooh. Hey, did you know the Wien bridge oscillator can make a sine wave all by itself? No input needed. There's only two conditions for it. The first one is
The startup condition. When you first power on a Wien bridge oscillator, it doesn't start oscillating right away. It actually needs a little help to get going. To kick things off, the amplifier's gain has to be set just a little bit higher than the losses in the feedback network. The extra gain will help boost tiny signals that are already in the circuit. And over time, the small signals will grow into a full sine wave. Now, if the gain is too low, the oscillation won't even start. It will just fade out. But if the gain is too high, the sine wave can get clipped or distorted, which isn't ideal. That's why, at the beginning, we slightly increase the gain, just enough to get the oscillation started, but not much as it messes up with the waveform.
Okay, so the second one is the sustained condition. Once the oscillation starts and the signal gets to the right level, the circuit has to keep steady. If it grows too much or dies out, it won't work properly. To fix that, the amplifier's gain adjusts itself and it lowers just enough to balance the feedback. That way, the waveform stays smooth and don't get distorted. The circuit usually uses things like thermistor, which change the resistance when they heat up to help control the gain. Diode can also be used to stop the signal from getting too big. All of that helps keep the sine wave nice and stable.
Let's explore the Wien bridge oscillator, a classic and widely used oscillator circuit known for generating pure sine waves. So, where is it used? Primarily, it acts as the sine wave reference oscillator in inverter circuits, which are essential for AC power supplies. It also plays a key role in test equipment like signal generators, helping to check and calibrate amplifiers, filters, and audio system. In function generators, Wien bridge oscillators provide a clean sine wave which can be shaped into square or triangle wave for border testing purposes. They are also widely used in audio signal generation, especially in 20 Hz to 20 kHz. For sensor simulation, they mimic analog signals to aid in sensor development and testing. What are the advantages? They are excellent for distortion testing in power amplifiers, useful in filter testing, and provide excitation signals for AC bridge circuits. But there are also some limitations, which is they are not suitable for high-resistance Wheatstone bridge measurements. And due to amplitude and phase shift dependencies, the output frequency range is limited. In summary, the Wien bridge oscillator is simple, reliable, and go-to solution for clean sine wave generation across many applications.
Today I will be explaining the important formula used in the Wien bridge oscillator. First, look at the three basic components, which are resistor, capacitor, and the operation amplifier, and the balance formula related to them, which is R1 R4 equals to R2 and R3. One key part of the circuit is the balance bridge. If the bridge is balanced, we then move on to consider the condition for substance oscillation. This includes a fixed gain and a specific feedback factor. Usually the gain is set using two resistors, and there is a standard formula for that. Now if the bridge is balanced and the component value are equal, we use the common formula to calculate the oscillation frequency. This is explanation how this formula is derived step by step. So that's the important formula that you should use for balance condition. Okay, however, if the component value are not balanced, meaning the resistor and capacitor are different, so we must use a more general formula, and this is how to derive that as well. So you can see how I derive this formula by including the basic three component, imaginary, and also the omega. So that's the important formula that you should use for the non-balanced conditions. So overall, this is an explanation of how this formula derived step by step. Okay, thank you.
Okay, so now that we understand the theory, it's amazing to see where the circuit is actually used. Its ability to produce such a pure sine wave make it incredible, valuable in many fields.
Absolutely. It's a star player in the world of audio. It's widely used in audio frequency generator for testing and measuring things like amplifiers and filters. It can generate pure sine wave across the entire hearing range from 20 to 20 kHz.
And it's not just for testing. The sampling sine wave is the starting point in many function generators. The oscillator provides the sine wave, which is then shaped by other circuits to create triangle and square waves. It also refers oscillator in sine wave inverters for AC power supply.
True, but it does have some limits. For instance, the maximum output frequency you can get is limited by the characteristics of the op-amp itself.
So, to wrap it all up, the Wien bridge oscillator is a fundamental circuit designed for one primary goal: to generate a highly stable, low distortion, sinusoidal waveform.
And it does this through a really clever design. It perfectly balances a positive feedback loop using the RC network to select the frequency, with a negative feedback loop that controls and stabilizes the amplitude of the final output.
Okay, that's all for us.
Bye!